Good morning. Am I audible?
Good morning, ma'am.
Morning.
Good morning, ma'am.
Good morning, ma'am.
Good morning, ma'am.
Okay, so last class we have discussed up to the starting of the Rankine cycle. So there we have drawn the PV diagram and TS diagram and HS diagram. So we have taken the condition of the steam inlet to the turbine heat, your wet steam and dry saturated steam, and there is the superheated steam. So in this case, the if you will observe, this is the um, this one is the condition of the turbine outlet. Okay, when it is the wet steam, then dryness fraction will be much lower than this exist from the superheated steam which is entering to the turbine. So this one is the pressure volume diagram. Then we have seen this temperature entropy diagram. Then we have seen the HS diagram. Then we have written the um, steady flow energy equation for individual components. So first component is the boiler, which the process is in 4 to 1. So there we have find out the heat addition is Q1 is your H1 minus H4, which is equation 1. Then in case of the turbine, we have find that by using the steady flow energy equation and considering the other energy is the negligible one. So in that case, the turbine work is found that Wt is equal to H1 minus H2, which is your equation 2. Then we have written for the condenser. In case of the condenser, there will be the heat rejection. So this one is the equation 3. So Q2 is your heat rejection. Pump is your, in case of the pump, we have to discuss what is the compression work required to compress the liquid water, which is the incompressible liquid. So, as you all know, in steam power plant, it will work based on the two phase of the working fluid. One is the liquid phase, another one is the vapor phase. Okay, so there, in case of the pump, we are requiring the compressor work, that is the pump work WP. So in this case, WP will be found out from the steady flow energy equation. So in that case, if we will use the steady flow energy equation, then this pump work will be written as it is the work conjunction. So here it will be X3 plus WP is equal to your H4. Whereas in case of the turbine, it was the output work. So there we were written at the right hand side. So that was the WT plus S2. So in this case, it is the work conjunction component or device. So that's why S3 plus WP is equal to S4. So here the pump work can be written as it is the H4 minus H3. So this one is the equation 4. So this is your pump work. So we have found out the turbine work, heat addition, heat rejection, and compression work or pump work. Now we can write down what is the efficiency of the Rankine cycle. So that is the eta R. So all of you know that efficiency of heat engine will depend upon the W net upon your Q1 heat addition, right? Um, Is anything happen? I'm not audible.
Ma'am, you are
Aditya?
audible.
Audible.
Ma'am, you're audible.
Okay. Okay, then Rankine cycle is here it is the heat engine. So in this case, we can find out the efficiency in terms of your output upon heat input. So W net means it is the difference of the work, that is your WT minus WP, right? So in this case, that one is the key, heat input is your Q1. So what is the turbine work? Turbine work is in terms of the enthalpy, that can be H1 minus H2 minus WP is here in terms of the enthalpy difference, that is the H4 minus H3. So heat addition is given as it is the H1 minus H4. Okay. So in this form also you can find out what is the efficiency of the Rankine cycle. This H4 minus H3, it will be find out in the difference of your pressure and as the specific volume. So in your last semester, already I have discussed to you this one. Again, I am discussing this thing. So maybe you have remember or not, we are writing the general property relation for the. So general property relations for ideal gas, which we have derived in entropy chapter. So that relation is your TDS is equal to your TU plus PdV, right? From this equation, we are finding out the what is the entropy change, right? So another property relation is your in terms of the, that is the TDS is equal to TH minus VdP. So here it is the pressure change. Due to the pressure change, what will be the specific volume change that we are going to find. So du plus PdV, this can be written as, this is the in place of the du we can write as Cv dt plus Pdv. So similarly, in place of the dH we can write as Cp dt minus VdP. So these are the two property relations for the ideal gas. So this equation can be used in case of the pump. So I have told you that this is the Rankine cycle, means it is the ideal cycle used for evaluation of the vapor power plant or steam power plant. So it is also known as the vapor power cycle. So ideal case means all the process will be the reversible one. Okay. So reversible means in case of the pump, it will be the reversible adiabatic compression process. Reversible. So in case of the pump, it is the reversible adiabatic compression process. So this pump will handle the liquid water, which is the incompressible one. So in this case, your density or your specific volume will change uh, uh, in small amount with the increase of your pressure. So in this case, your pressure will increase due to the compression, but this change of the density and specific volume is much smaller than this increase of the pressure. So in this case, for the reversible adiabatic compression process, so we will use the property relation, that is your TDS is equal to your TH minus VDP. So here it is the pressure change, right? So pressure will change from the P1 pressure to P2 pressure. Okay. So if we were writing the pressure change and that enthalpy change and what will be the specific volume that I can write as so it is a reversible adiabatic compression process, right? So reversible adiabatic compression process में ये आपका zero हो जाता है. So this will be zero means your DH is equal to your VDP. Okay. DH is equal to VDP. So since your specific volume change is a negligible one, so this can be written as delta H is equal to your V delta P. Okay, so delta H means in case of the pump that will be written as H4 minus H3. So this V specific volume will be your V3 volume. Okay, V3 into your pressure change will be the P1 minus P2. Okay, so the pump work can be represented in terms of your V3 into P1 minus P2. So अगर प्रॉब्लम में आपको प्रेशर ही दिया गया है, then you have to find out what is the pump work. So in that case, what you will do, so as per the pressure P2, you have to find out what is the V3. V3 is nothing but it is the VF3, right? VF3 find out करेंगे तो V3 मिल जाएगा. Then you can find out what is the pump work, that is the WP. ये भी आप find out कर सकते हैं directly without using this enthalpy, that is your H4 minus H3. है ना? So in this way you can find out your pump work. So in case of the turbine and pump work, if you will compare, so pump work, that compression work is small as compared to your turbine work. Sometimes what we are doing, this H4 minus H3, we are neglecting this difference. We are neglecting. Why? Because H4 is equal to H3. Okay, so sometimes because in this case the volume change is small and sometimes this one that change we are considering the negligible one as compared to your turbine one. So in that case ये जो आपका efficiency relation है, so in this case this work we are neglecting. Okay, so let us write this relation is it is the equation number 5. Then this equation number 5 will become as the efficiency of Rankine cycle. We can write as it is H1 minus H2 and H1 minus H4. It is the heat addition, it is the turbine work. So sometimes when your pump work is quite small as compared to your turbine work, so in that case, what we are doing, that turbine pump work we generally we are neglecting. Then in that case, we are writing as H4 is equal to H3. Then your efficiency can be written as that is your H1 minus H2 upon H1 minus H4. Okay, so this is the case we can say that it is where your pump work is much less than your turbine work. Then in that case, Rankine cycle efficiency can be in this one. Okay, so you can also find out your network by using your uh, TS plot. So we can draw that diagram. We can find out the heat addition and heat rejection in case of your TS plot. So I have taken the superheated steam. So 1, 2, 3, 4, 5, 6. Okay. So if you will observe this TS plot, your Q1 is your heat addition and Q2 is your heat rejection. So Q1 can be represented by the proportional to the area. What is that area is your 1564. So that is the area under this curve. So that is your area 1564. So similarly, Q2 heat rejection can be represented as it is the area under this process. So that is your 2563. Okay. So similarly, your W net can be represented with the help of your area. So that W net is nothing but that is the Q1 minus Q2. So if we are neglecting this whole area, this one, then we will have the net work will be this much. Okay, so this is the W net. So area within the process diagram is nothing but it is the uh, network output. Okay, so network output is proportional to the area 1, 2, 3, 4. Okay, got my point. So in case of the steam power plant, the capacity of plant generally we are also finding out capacity of steam plant. So that capacity of the steam plant is represented in terms of the steam rate. Okay, tell me, do you have any issue?
No, ma'am.
Who has raised the hand? Venkata. What is your problem, Venkata? Tell me. Hello. So don't disturb me like this, okay?
मैम
Okay, tell me, Ankit.
मैम कैपेसिटी ऑफ स्टीम पावर प्लांट का मतलब क्या होता है?
कैपेसिटी है आपका जो कितना स्टीम कंजप्शन हो रही है यूनिट शाफ्ट आउटपुट के लिए, तो उसको हम बोलते हैं कैपेसिटी ऑफ स्टीम प्लांट। कितना स्टीम कंजप्शन होनी चाहिए, स्टीम फ्लो होनी चाहिए। स्टीम पावर प्लांट में आप जनरली कोल यूज करते हो, तो उसके लिए वो जो स्टीम फ्लो होती है जनरली टरबाइन में, उसको जो जनरेट के लिए उस उसको हम कैपेसिटी ऑफ द स्टीम प्लांट बोलते हैं। So it is also known as the steam rate. So by definition, if I can say that I'm writing that one rate of steam flow. So rate of steam flow means it is represented in terms of the kg per hour. Okay, steam flow required to to produce unit shaft output unit shaft output, that is unit towards output means आपका 1 किलोवाट टर्बाइन में जितना अगर 1 किलोवाट नेट वर्क आउटपुट हो रही है तो आपका स्टीम फ्लो कितना हो रही है उसको हम कैपेसिटी ऑफ द स्टीम प्लांट बोलते हैं. So that is also known as your steam rate. So steam rate by expression if you are representing, so it is 1 upon Wt minus Wp. So this is the network output. So we can say it is I have taken the unit flow of the steam. So uh, so if we are writing the unit of this Wt and Wp and also this 1 kg per hour, so sometimes that unit can be represented as kg kilowatt second. So if it is represented in terms of the kilojoule per hour, then it can be repeated as 3600. This is Wt minus Wp. The unit will be in this case will be kilojoule per kilowatt hour. Okay, so this is your steam rate. To find out the steam rate, you can use this equation. So which is in the unit maybe in this term, that is a kg per kilowatt second, or it may be kilojoule per kilowatt hour. So as for your problem, you can use the equation. So sometimes the cycle efficiency, the Rankine cycle efficiency can be expressed in terms of the heat rate also. So heat rate means it is the rate of heat input, that is your Q1, right? Required to produce your unit work output, that is a 1 kilowatt of your work. So in that case, that heat rate with the expression, if I am representing, that is your HR. HR is equal to 3600 Q1 Wt minus Wp. Okay, so it is also written as it is 3600 upon theta R. Okay, or it is the cycle efficiency. The unit will be the kilojoule per kilowatt hour. Okay, so it is your heat rate, and this one is the steam rate. So if you have remember, I have discussed to you that reversible adiabatic. Reversible adiabatic work done in steady flow system. Steady flow system, right? So steady flow system means as it is the ideal process, so that's why we have taken it as it is a steady flow system. In that case, if you have remembered, we were using the steady flow equation, that is your सब एनर्जी इक्वेशन का हम यूज करते थे, dq is equal to dh dw, right? So that equation जो है आपका, और एक क्या था, ये है आपका वर्क का था, और एक था टी एच, इट इज वी डी वी था, राइट? और क्या था, जी डी जेड, है ना? ये हम इक्वेशन यूज करते थे स्टेडी फ्लो सिस्टम में इन डिफरेंशियल फॉर्मेट में. इसको डिराइव करके, इसको इन प्लेस ऑफ द टीडीएस हम क्या लिखते, डीक्यू में हम क्या लिखते थे, डीएस लिखते थे, और फिर ये इक्वेशन लिखते थे. So after that, what we will find out in that case, that work done is equal to, that is your integration of your VDP. याद आया? So here it is the pump work, so that's why I have written it is 3 to 4. Reversible adiabatic work done in steady flow system. So here it is the pump cases I have written. So that is minus integration of your BDP. So from this equation, if we can see that your work is closely associated with your specific volume change, right? It is related to the specific volume and your pressure change. So larger specific volume will give you the reversible work produced or consumed will be the more larger. What I mean to say, यहाँ पे आपका अगर specific volume ज़्यादा है, so in that case your work produced or consumption will be larger from this equation. Okay, so in case of the compression, in case of the pump work, to minimize the pump work, what we are doing, we have to minimize the specific volume of the fluid. So it must be as much as small so that your compression work can be reduced, or we can minimize the work input to the pump. Okay, so but in the expansion process, that specific volume is increased. So in that case, your specific volume is larger, so that we can get the um, maximum work output from the turbine. Okay, so that is the reason why your steam power plant is much used in case of the power generation. The reason is that in case of the pump, we can use the smaller specific smaller size of the pump, so that the pressure rise in the pump is nearly equal to your pressure जो ड्रॉप हो रही है टर्बाइन में उसके साथ सेम होती है, राइट? ठीक है, तो in that case it can handle the very small specific volume of liquid, whereas your turbine can handle uh, turbine can handle before specific volume is many times larger than the pump. Okay, so एक बात देख लीजिएगा, ये टर्म इसको हमने डिटेल में नहीं बता रही हूँ, ये हम लोग फाइंड आउट करते थे रिवर्सिबल adiabatic work done in steady flow system. Okay, so next one is the actual vapor cycle. So in Thursday class, what we will do, we will solve some problem related to your vapor power cycle. That is your theoretical cycle and your actual vapor power cycle. Okay. One, oh, sorry, here one here. Two, three, turbine can let one, then turbine processes one to two. This is your condenser. A condenser will process two to three. Okay, so then it is four. Okay, so in this case, your okay. So in case of the actual vapor cycle, we will consider the losses. Generally, the losses are included your fitting losses or piping losses. So if you are observing this case, we will have the pipe connections. So and that pipe will be connected to the component with the help of certain fittings. So due to the piping losses or fitting losses, so maybe there are some leakage in fitting. So if we are considering that losses, then your efficiency of Rankine cycle will reduce, and it will depend upon the turbine efficiency, and it will also depend upon the pump efficiency. Okay, turbine efficiency and your pump efficiency. So if you have remembered, there we are using some isentropic work, right? And certain ideal work, sorry, actual work. Okay, compressor efficiency or it is the pump efficiency. Okay, so here it is the flow diagram of your vapor power cycle. So here if we are considering the losses, so in that case the certain heat will be losses when their steam is going to the turbine inlet. So that heat loss I can take, that is a Q loss. Okay. So similarly, there must be due to the blade uh, arrangement, different rotary components are there. So there may be some heat losses also, that is considered as the Q loss. So in case of the pump, there we can experience some heat loss also. And in this case, in this pipe also, in this fitting also, we will experience certain losses. So due to the losses, so whatever the pressure will, pressure should achieved in ideal case, that will not attend in case of the actual process. So what will happen in this case? Certain pressure losses will be there. So that pressure losses is generally achieved in case of your piping arrangement. So if you have remembered that turbine efficiency we were considered as turbine work we were considered as that is your um, H1 minus H2 minus your Q loss we were considering. Okay, so in that case your turbine work or turbine efficiency we were finding out turbine efficiency. Turbine efficiency we were finding out that is your H1 minus H2 that is your upon your H1 minus H2S. So H2 is nothing but it is the enthalpy change during your please wait for me. Sorry for the disturbance. Hello.
Yes,
There
ma'am.
is okay. Okay. Thank you. Thank you. अब ये गुप्ता जी का नंबर ना ठीक है ओके थैंक यू मैं चेक कर लूँगी मैं sorry for the disturbance. It was an important call, so that's why I attended. So in this case, if you will observe, H1 minus H2 is nothing but it is the actual turbine work. So actual turbine work it will consider the losses in the process, and it is H1 minus H2S means it is the ideal turbine work. So ideal turbine work will related to the isentropic enthalpy drop. So it is an isentropic enthalpy drop. Isentropic process will be considered reversible adiabatic process. Okay, and but in actual turbine work, there we will not consider the reversible adiabatic process. So the process will be the irreversible one. So if I will plot that diagram, then it will be TS plot will be like this. It is difficult to draw with the help of this digital pad. One, one, two S, three, four S. So sometimes the okay, so it is in case of their pump. So it may be the turbine means the work will be. So sometimes it is 2 or 2 days. It will depend upon the entry condition of your steam. So this is your mm, if we are considering the losses, so these are the due to the losses, your expansion will be like this. So it is your H1 minus H2, and it is isentropic means it is H1 minus H2A. So similarly, in case of the pump also, we will consider the actual work and your turbine, actual work and your isentropic work. So if we are considering the pump losses, so these pump losses will be similar to your turbine cases. So the process will be the actual process will be the irreversible process one. So that irreversible process will generate due to the fluid friction. So in this case, the heat losses will be there in case of the piping, and that pump efficiency can be represented as eta P. So which is equal to your it is your ideal upon your actual. Okay, so ideal work means the pump work generally we are representing H4 minus H3, right? So ideal means here we will consider the isentropic enthalpy. And in this case, actual case, that will be the H4 minus H3. So a WP, this will be the H4 minus H3 will be the actual pump work, and in this case, it is the ideal pump work. Okay, so in case of the actual paper power cycle, we have to consider the turbine efficiency as well as the pump efficiency to find out the efficiency of your Rankine cycle. Okay, so in Thursday class, what we will do, we will solve some problem related to your losses as well as the ideal condition. So that day I will not discuss related to this theory, only we will solve the problem. So that day all of you please be prepared, be ready with the steam uh, table. You may have steam table book, so please keep it with you and we will solve some problem. Okay, so up to this I am discussing. Thank you all. So today's attendance, Jyoti or Ritika, please send to me. Okay, I am not taking.
Okay, ma'am.
Okay, so there are only 84 students. So that much only we have to send. Okay. Okay.
Thank you.
Yes, ma'am.